thermal fluid sciences experts. This is Pro Ready Engineer.
Well, hello again. This is Bassam Abdelnabi from Pro Ready Engineer. We are gonna today go over the conservation of energy. Very important principle and concept. It comes with different flavors. They are all the same, but simplified versions. You've heard about Bernoulli equation. It's essentially an energy equation with some assumptions. And also you have seen this in the first law of thermodynamics. You've seen this materials scattered in your fluid mechanics courses, in your thermodynamic courses, in advanced courses, turbomachinery, HVAC. Highly unlikely you don't come across or use this, whether you are an advanced engineer or you are a student of engineering or you're anywhere in between. This concept is extremely important, not only to know the equation, but to build a feel for the equation. My goal is not to only teach you a topic, but it's actually beyond that. More important is to build that feel. So let's get on it. And always remember that things that are complex, the reason they come across as complex is you don't understand them. But essentially, once you understand, complexity goes away. And this is why when somebody tells you like a very good idea, once the person tells it to you, or once you hear about it, you immediately say, oh, it just makes perfect sense. It's common sense. It flows smoothly. And this is everything in our lives. It flows smoothly as long as we understand. And it gets extremely difficult and frustrating and wastes a lot of time if you don't understand. Typically, if you look at my videos, you see that I follow a very slow pace. I spent close to 2 hours on these videos I make. And my philosophy is you can spend a couple hours learning something slowly, deeply, with all the details, but look at yourself when you execute how good you will be. I have worked with many engineers in my career, and I'm going to put it this way, they would have been much better engineers if they had that level of depth and understanding and common sense. Let me tell you, those things that I focus on and the little things here and there, you always listen in my presentations and talks as I share some of my experience with you. I almost can tell you, after working and knowing hundreds, if not thousands, of engineers, that few, truly few, I may be able to count less than 10. Less than 10. Do you imagine somebody who's been working for 25 plus years in the field, and then I tell you less than 10 have that level of deep feel and connection. So I'm going to change that. By these materials I'm publishing, I'm going to change that. I'll bring, I'll communicate that. I'll teach it early on to people. Doesn't matter who's listening to me. If you are a 60 years old professional engineer, I think you'll benefit a lot from my material. as well as if you are just a student of engineering, because when I go over a topic, as you've seen in my previous videos, I go from zero to hero, right? I take you from zero to hero. You will see that, for example, today, I'm gonna start with the basics of the energy equation, but there will be more to come to make it advanced. On the screen here, this is just a brief. You can always go to Google Scholar and find my publications in technology and science. I have my patents here, a little bit more information about me. Okay. So what is it that we are going to be discussing today? Let's grab a pointer. The way we are going to do this is we'll start by what you know and what motivates us. Why would we want to study the conservation of energy? We move on to bolts and nuts. Any topic you break down to the bolts and nuts, you see, how many human beings, if you give them a bolt and a nut, they wouldn't be able to, spin the nut on the bolt? I think very few. So if you start from the bolts and the nuts and you assemble all the way up, by the time you reach to this big assembly, it's common sense. It's simple, easy to understand and comprehend. So that's exactly the flow, right? We'll start with some fundamental quantities, properties, things of this nature. Then we move to introduce mechanical devices that are used for energy conversion. And we are building toward this section 4. Section 4 is typically where you sort of start learning this topic in regular teaching styles. I don't believe it's an effective way. I think this way is truly very effective, that I am teaching you about the topic. So by the time we write down the formulas, it will feel to you as if these formulas is something you've known forever. They are very easy, very simple to write down. Then we will give some conclusions. And as I always say, I'm going to take you from zero to hero, from the very first principles of how we think about conservation of energy. And down here, I'm going to take you to CFD analysis, what kind of different CFD exists, why we use them, how we use them, what's the value, what's the assumptions. I cannot do all that I need many hours. So what I'll do is I'll cover this today, and then we'll go to the next level in either one or two videos that will come really soon, if you will. Here's a depiction of what I was just talking about. We start with the properties, a little bit, individual things, bolts and nuts. We put them into system components or, type of machines, if you will. Then we go to formulation, equations, and things of this nature. After that, which is the next video or two, we talk about cycles. Then we talk about the detailed and advanced form of the energy equation, how it gets solved, why we need to solve it, what we get from it. It will be a lot of fun. Okay. To set you up for success, you see, conservation of energy is a concept that you come across in your day-to-day life, and you either notice that or you don't know that. So let me tell you. See the fan that sits on your desk. What is this fan doing when you turn it on? What exactly happens? You say, it blows air on me. That is conservation of energy. How is that? Well, you see that rotating element that rotates. It took this rotating mechanical motion and transferred it to fluid motion. Your water heater. What does your water heater do? Burns natural gas. You know there's a natural gas connection. Many of you went probably in your basement. You've seen the little flames there. And it takes this natural gas and take that energy and heats up your water. That's conservation of energy. Your air condition, your fridge, your car engine. Car engine, you put fuel and you get your wheels rotating and you travel. Mechanical motion from fuel energy, conservation of energy. The jet engine, when you fly, that device on the wing that powers the plane. Principle of, conservation of energy. Steam turbines that generate electricity. If you've never heard about them, these are very important units that, they generate electricity. We're going to talk about them in this presentation. And on and on and on. So either you notice that this conservation of energy, where the energy is changing from one form to the other, or where it's changing from something to something else, to function in a certain way, to deliver a target. This is all governed by the conservation of energy. So it's a key ingredient. We need to know it well. We are going to get on it, starting by the very basic bolts and nuts. We're going to talk a little bit about conservation, concept, properties, heat transfer, fluid flow, work, closed and open systems. So let's do that. In every section, I'm going to follow the same strategy, if you will. I give you the name of the section and the ingredients or the components of that section, if you will. I'm going to strongly advise you to go back to my video about properties. Watch it first. I have like a slide here, but I think the video is like an hour and a half or something, talking about the properties, how to feel them, how to measure them, I got a tremendous amount of positive feedback from people who have seen the video, so thank you for that. Always remember when you watch my materials that I am actually following a sequence. It's not haphazard. I publish something and I build on that, and I kind of keep doing that. So very quickly, a refresher about thermodynamic and flow properties. U is internal energy. Think of it as the energy of the molecules. It's something that, very strong function of the temperature. Enthalpy is similar to it, but it's a little bit more than that. It's not only the internal energy, but it also has what we call the, flow energy, PV or P over rho. V is the specific volume. Specific volume is 1 over density, as you've seen in my other presentation. I'm not going to say that again. Just please review the presentation and the video. Enthalpy relates to open systems, as we're going to talk today. And essentially what that is, it's very simple. It's if you have fluid flowing, fluid is flowing, going into something, exiting something. This is called fuel flow. So when the fluid flow. Fluid flow. So when the fluid is flowing, you work with the enthalpy. This is the thing you use to express the energy with that flowing fluid. You express the energy. It's like I tell you how much money you have. You say I have, $250. That's it. That's the enthalpy when you are going into or flowing out from a study or a device or something you're interested in studying. Concept of entropy, a measure of disorder. Pressure, force per unit area. CV and CP, specific heat. The energy required to increase the temperature by 1 degree. Mass flow rate, the amount of mass flowing per unit time of the fluid you are working with. and v is the velocity. I'm going to put the link in the description for you to learn more about these properties. In the other video, I did not discuss these concepts on the screen, so let's get on it. Before I talk to you about conservation of energy, if I'm going to teach you about conserving something, you better know first what is the something. Enthalpy is one of that something. It's the energy of the flowing fluid. We discussed that. Now add to it potential energy. Potential energy, you've taken it in your high school courses, where they told you MGH, right? There's a datum, you take something, you go from the datum. They told you when you're standing there, the energy, the potential energy you have is MGH. So where is the mass here? Why didn't you put mass, M or M dot or mass flow or something of this nature? Because this is just a specific energy form. What do you mean specific energy? Well, that's in joule per kilogram, energy per unit mass. We many times like and use both flavors. The flavor where we say, here is the energy per unit mass. And then when you say, no, here's actually the total energy. So you multiply that by the mass. So the units of that is joule per kilogram, kilojoule per kilogram, BTU per pound, energy per unit mass, and it's also, this reduces to feet squared per second squared, meter squared per second squared, and on and on. Likewise, kinetic energy. Kinetic energy, potential energy, is easy to build a field that there is energy. If you don't feel it, it's actually relatively easy. Take something like I'm here, for example. I'll take my phone. I'm gonna put it here. If I don't trust that there is potential energy, I'm gonna let my phone go, and when I let it go, it's gonna run and go down. That energy, when it ran and go down and hit the table, this is essentially potential energy, MGH. And v squared over 2 is the kinetic energy. It relates to the velocity. mv squared over 2 divided by m, that's specific. Kinetic energy is simple to build a field for. A vehicle hits you while it was traveling at 5 miles per hour. No big deal. You'll be doing great. A vehicle hits you at 70 miles per hour. Very low chance you will survive that. So what's the difference? Well, when the vehicle hit you, it had an energy of mv squared divided by 2. So when the velocity was very low, nothing happened. But when the velocity was very high, it had tremendous amount of energy that got transferred to you at the moment of impact. And imagine if we subject your body to that, it's beyond what your body can take, essentially. Now, this and that, the v squared and the gz, the potential and the kinetic and the enthalpy, they relate to the mass flowing. The mass flowing, it has either kinetic energy, potential energy, or enthalpy. This is all the things a mass can have in it, nothing more. It's like I tell me the different type of money you can carry. You say it's either gold or cash or properties. That's it, something of this nature. So there's nothing else that can express the amount of money you have. Now, another form of energy is Q. Now, this doesn't need mass. Q, heat, doesn't need mass. Q is the energy that flows because of a temperature difference. Best example I can give you of what that Q is you take a pot with water on it, you put it on the stove, you turn the stove on, right? If you go and measure the temperature of the water, you'll see the temperature is coming up. And all what's happening is this fire you have is transferring this heat into the water. That thing that moved and heated the water is called Q. Capital Q is in kilowatt, megawatt, BTU. If I put a small q, that's a specific one. That's the kilojoule per kilogram, BTU per pound, and so on. And take note so you don't get confused. I put this here per unit mass, and I put this here as a total kilowatt. I could have just put it in as kilojoule per kilogram. Doesn't matter, really. I wanted to put intentionally both flavors on the same slide. Okay, we're done with Q. We're done with Q. Work relates to something that moved. The very first time they educated us about work was that work equals to force times distance. If there's no distance, there's no work. Work is zero. You tried to push something, you put force on it, but it didn't move. Well, that's a work of zero, right? Work, for us, when I say us, are engineers. To the most part relates to a spinning shaft. Now, that concept of a spinning shaft, I want it to be engraved in your brain. We love a spinning shaft. It's not exaggeration to say that almost all is like 90% of the engineering devices, involve mechanical motion, mechanical engineering devices, have a spinning shaft. Your vehicle has a spinning shaft. Your fan at home, that's a spinning shaft. The turbine generating power in a power plant, that's a spinning shaft. Your bicycle, spinning shaft. And on and on and on, there is a shaft spinning, doing something. Compressors, spinning shaft. Pumps, spinning shaft. Wind turbine, spinning shaft. You name it, spinning shaft. What does spinning shaft mean? That's work. This is work. This work doesn't need mass. That spinning shaft is just a solid spinning shaft. It's called work. And it's, units are going to be power units, kilowatt, megawatt, BTU, and you can divide by m dot or m and say, well, this is specific now. Joule per kilogram, BTU per pound. Okay. I want to talk to you about something down here. Now, in your basement, we discussed, you have this water heater. You know heat transfer, you know Q, because it's in your basement. The natural gas is burning, the flames are burning, and heat transfer to the water heating it up. So you know what is Q, right? A fan takes electricity to spin a shaft, and then that shaft pushes the air on you so you feel comfort. The opposite of it, is a wind turbine. A wind turbine does the exact opposite. The air blows on a wind turbine, spins it, and you take work. In this case, you take work. In this case, you pay work. Though this is air and this is air. But the need is different. Very interesting. We discussed open system versus a closed system. To the most part, everything is open system. To the most part. Whenever I use the word, just so you now know more about me, whenever I say something and I say, well, this is what it is, this is what it means, that 90% of life is what it means. Are open systems, right? Open systems, what do you mean by open system? Very simple. What is system? System is that thing you are interested in, you are solving. If we are analyzing your fan, then your fan is our system. That's it. If we are analyzing your water pump, that's our system. A turbine, that is our system. Your boiler, it's our system. That's system. Open system means there's a mass flowing in and a mass flowing out, or just in or out. There is mass flow. That's an open system. So when I say that, the first thing that comes to your mind, well, everything is almost, very few applications is, where no mass goes in and out. So then we shouldn't have closed system? No, there are closed systems. What happens in a closed system is there's no mass transfer. Mass doesn't come in, mass doesn't go out. Now, it doesn't necessarily need to be all the way. See, your car engine, the way it runs, this is a little bit beyond what we are going to be discussing today, but I'll tell you that here because I want you to understand that. The way it operates is, it operates on what we call a cycle. For now, no, a cycle is something happens, then another thing, then another thing, then another thing, and then we repeat again. What happens in your car engine is a portion of this, not the first one, is closed system, is the right approximation. Something happens, something happens, something happens, and it's closed. There's no mass coming in or out. When we go to analyze that part, we analyze it as a closed system. So now you understand that when we do an analysis, it may be we are just analyzing a part of a process that is actually at that moment closed system, and we analyze it using a closed system formulation. Why are we dividing the systems into open and closed? Because our analysis will be a little bit different, by the way. That's it, that's all, just a little bit different. Good. And I have some depictions here. Open system, open system, open system, stuff coming in and out. And a cylinder here with no mass transfer is a closed system. Good. So what is conservation? Conservation is a common sense principle. All engineering, remember, engineering is an applied science. It's using science to do things that are useful to our lives. This is engineering. And it all makes perfect sense. Engineers, in my opinion, I would recommend every single human being on earth to study engineering, one way or the other, even just a portion of engineering, even if you get another degree, even if you are a medical doctor. Engineering is amazing in making your thinking structured and geared toward targets and efficiency and economy. It makes you think of multiple things at the same time, very well organized at what you do, and it benefits all aspects of your life. Conservation is a concept that you know by heart. You know by heart. You say, earlier in the week, I had $1,000, and now it's Sunday, and I have 350. So what happened? Just 1 second. Well, I spent 650. There's nothing else to say. Likewise, when we do the conservation of mass, and energy will follow, the mass going into a system is the mass coming out plus the mass that was stored. no one can object to this equation. And you can never forget it. Like I tell it to you now, and until the day you die, you cannot forget it. Because how would you forget it? It has to be like God forbid you lose your brain or something. What comes in has to be what comes out, that what was stored. Now let's look a little bit more into it. Let's say you have this garden hose, right? Do you think that this garden hose is storing mass? That would be funny. You turn the faucet on. We all have garden hoses. You turn the faucet on, and all what happens in the hose is water comes in, water comes out. So the mass flow of water coming in has to be the mass flow of coming out, and there is no stored mass. This is an application where stored mass has no value. Don't even talk about it. Mass comes in, mass comes out. Now, if we talk about filling your pool, that's a little bit different. Your system in this case, what you are analyzing, what you are designing, is your pool. You are filling it. That's my pool, that's my system. Okay, what's happening to your system? You say, mass is coming in, your hose is on, you're filling it. No mass out, and the mass is all stored. The mass in is what is stored in the system. So you cannot go to analyze this and estimate it and do some equations or formulations and say, well, there is no stored mass. The whole thing is stored mass. Good. So conservation is actually very simple. So now let's move, before talking to you about conservation of energy, I've given you all the bolts and nuts we need for now. I'm going to introduce you to mechanical devices. We need that before we move forward. What are the mechanical and energy conversion devices I want to share with you about? We have the turbines family. We have the compressors, pumps, and fan family. We have the boilers, heaters family. We have the condensers, radiators family. We have the throttling valves. We have the nozzles and diffusers. These are devices that exist in everything around you. Let's see what they are and what they do. Turbines. These are devices, mechanical devices, that harness energy from energized fluids. If you have a fluid that is energized, that have energy, you put a turbine and you extract that energy. What do you mean extract the energy? You put that turbine and you get that spinning shaft we are talking about. And once you get a spinning shaft, somebody is spinning the shaft. The turbine is spinning that shaft for you. You can do a tremendous thing with this. You have seen water turbines before. I've seen a lot of ads on Facebook and on YouTube of units being sold now. They go to a river. They have this set of blades. They put in the river, and the river is flowing, so it's spinning. It's connected to a little generator. And then they have generated power. It's a turbine. It's a water turbine, but a micro turbine. It's a very small turbine. But that's the whole concept of turbines. It takes the energy of the flowing river that by itself is not very useful to you, and suddenly makes that something that is actually very useful. That spinning shaft connected to a generator in this case. You see, when we were kids, they used to sell a unit that is that size of, it's about 3 inches long, 3-4 inches long. It's a generator that we used to hook up on our bicycles. Now here's what it had. At the top there was a little wheel, and we would install it such that this little wheel is touching the wheel of your bicycle. So when you pedal and your bicycle spins, that generator spins, and from that generator there were a couple wires coming out going to a light that you hook up at the front of your bicycle, and there you go. As you pedal, you have light that you will never run off. The battery will never go down because it's using a little bit of your pedaling to give you that light that you need. This is how, when we have a spinning shaft, we can change it to electricity. You've seen that concept before of a generator generating electricity when something spins it. In that case, you're spinning it with your foot, right? Well, in this case, water is spinning it for you. Much better than you having to pedal to spin. Hydraulic turbines, you've heard about dams. You've seen many videos, you've seen pictures, these tremendous structures, you've seen them in the movies that have tremendous amount of water behind them. What's going on there? It's a very nice concept. You know, all this tremendous amount of water, we get it through runners, tubes, and as the water comes down, you see how the water, when it comes down from a fall, right? They tell you that if you fall, that's a, you know, if the fall is a large fall, there's a very, you know, low chance you will survive that. So that tremendous amount of water flowing, we put these, you know, spinning wheels in it, and the water hits it and it spins. And there you go. We take it, we hook it up to a generator, we generate electricity. These dams, they have turbines that generate electricity that comes to your home to power your devices. So what is a steam turbine? It's similar to water turbine, but it uses steam at high temperature and pressure to spin a set of blades to generate electricity again, for example. See, the steam comes in, you see these little blades, we call these little blades, right? And it spins, 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 and now you have a rotating shaft. Hook it up to a generator, now you've generated electricity. Steam turbine. Wind turbines, you've seen them. They are, you know, when you're driving on the highway here in the US, or if you are in Europe, you've seen a lot of them. And in many other countries, you've seen them, but many times they are not in, you know, crowded city areas. They need to be a little bit outside, and so it depends on where you are. But these devices does the same exact thing. Wind is blowing, right? All right, we're going to make it spin, shaft, generate power. Gas turbines. Gas turbines, they convert the energy of fuel to mechanical motion, like the jet engine, right? And think about it. If I bring you a bottle of fuel, it's a bottle of fuel, I cap it, has natural gas in it, and by itself, this is useless, like it's sitting, you know, we human beings want to, you know, make use of that, use it for our needs, use it to help us achieve something. Now, that fuel, if you don't believe me that it has energy, a lot of energy in it, you can just open it up and light it up, and it may not be a very pleasant, so please don't do that. A better experiment is go to your barbecue grill that runs on propane and turn the propane on, and, you know, stand there, hold your ignition system, whatever that is, and you see it's, you know, colorless, you don't see the propane coming out, but you probably can smell it, and light it up, and boom, it lights. This is because it has stored energy in it. Now, these devices, what they do is they take this energy from the fuel and give you a spinning shaft for you to do something with it. Gas turbines. So there you go. When turbines are used, they are used for two reasons. Either, like I have said, connected to a generator, generate electricity, or actually use it as a prime mover just to spin something. Now, for the fun of it, there was an attempt, I'm not going to go into the details of what, why, and when, but to power a vehicle with a gas turbine. And think about it, that's not primarily generating electricity, right? What we need in this case is, you know, the shaft is coming out, it's spinning your wheels now. And we've transferred this energy to it's a mechanical drive, it's driving something. Another usage, now this was not successful for many reasons. There's no need to discuss that now. You can Google it. Please do your own research on it. But we can use these turbines to spin compressors, for example. See this compressor we were talking about a second ago, like your pump, your fan. This compressor that is used to pump gases. In your home, you have natural gas. To the most part, you may have. Many of us do, at least, let's say. Where is natural gas coming from? Well, the answer is somebody is pumping it through a gas line to your home. How are they pumping it? They have a compressor installed on the line, pumping that gas, giving it that energy it needs to travel and come to your home. These compressors, someone needs to spin them. Now, for sure, we're not going to hire someone to stand there and do this. It's not feasible, nor will they be able even to do it. It needs a lot of power. But we put a turbine. We get a turbine, hook it up to that compressor, and there you go. It's spinning it, and now it's pumping the thing that needs to. That's called the mechanical drive. Mechanical drive means I'm using this turbine not to generate electricity, but to do something that relates to a mechanical motion, if you will. When we depict these turbines to analyze them, we many times use a simple schematic as down here. So here's the turbine, it's coming in at 1, this is coming out at 2. This is, for example, the hot gases coming in at 1, the steam coming in at 1, and so on, and leaving at 2 after we have extracted this energy, and that's a spinning shaft right there. We've been talking about spinning shaft to give you work. Good. Let's move on. The second set of mechanical devices I want to introduce to you, compressors, fans, and pumps. We lump them together because they do the exact opposite of the turbine. You need to spin them. They take work to pump something. You are sitting at your own home. You don't feel well. It's a bit hot, reasonably hot. And you turn your fan on. So what is it exactly doing? This motor is giving work, is adding work, and then the blades, as they move, they transfer this work and push the air. They are pushing that air. Now, you say, well, if a fan pushes the air, why is it different than a compressor? If you said that the compressor also pushed the gases, very different. Compressors are used when we want to build pressure. You need pressurized air. Now you need a compressor. Fans are not used for that. Fans are used. What do you need a fan for? Do you need a fan for pressure? No. You need a fan for kinetic energy, to just blow the air on you. Now, compressors, we use them to pressurize the air, to have air, or for that purpose, or natural gas, or whatever the gas is. Compressors, they give you energized gases at high pressure. And I will tell you more about kinetic energy and pressure as we proceed more about the compressors. I think there may be, I can tell you a little bit more. The pump is very similar to the compressor. Pump is similar to the compressor, but it pumps incompressible fluids. You have a water pump, a fuel pump, an oil pump. Incompressibles, they get pumped. Let's say we want to take water from the river. In your own home, you get water, you open the tap and the water is flowing. Where is this water coming from? Well, there's a river somewhere, and there's a pump that sucks this water from the river, adds energy to it, and now it's pressurized water. It can flow in a pipe long distances and come to your home. There will be a tank in the middle of that, but that's not our discussion here. But then it comes to your home. That's a pump. Adds energy to the water, in this case a water pump, oil. In your vehicle, you have a gasoline fuel pump. When you switch your ignition key to on but you don't start the car, you hear a humming. That humming is your fuel pump priming and saying, hey, I'm running. This is why actually when your fuel pump goes bad, that's the very first diagnostic you do to know, my car is not starting. What's going on? Trying to start it today, I hear it trying to crank, and everything appears right, but it's not starting. You put it on ignition and you listen, and now that humming you've been listening to for many years is not there. It's not humming. Well, there you go. You need to go and just put in a new fuel pump. This pump takes the gas from the tank, sends it to the engine. These are pumps, what they are made for. Good. So now we know compressors, pumps are found in the same family. They take work to energize fluids. We tend to sketch the compressor this way. Goes in through one, compresses, leaves at two. We pay work for that. We have to pay work for that. There's a reason for the compressor to be plotted this way. And you've probably noticed it's the opposite of the turbine. And I want to share that reason with you. See, compressors, I told you a second ago, are there to increase the pressure of the fluid, air, for example. So let me ask you, if you write down the mass flow rate equation, we all know that m dot is rho VA. If m dot in this device is constant, m dot 1 is equal to m dot 2, right? The mass comes in, mass comes in. That's why you have a compressor. It takes the air, pumps it, gives you the air. No stored mass. I have applied the mass conservation. If m dot is constant, it's equal to rho VA, and for now accept from me that V is constant. And when you take your turbo machinery, I'll probably be one of the things on my list. Again, I told you I'm following a strategic plan of how I am releasing these materials. So there will be something coming in turbo machinery. For now, V is constant, and just accept that for a second. Well, if V is constant and rho times area is constant, if this is increasing density, rho is increasing. We said that we are increasing the pressure of the air, and rho is equals to P over RT. What happens to the density when the pressure goes up? Density goes up for gases. If the rho is coming up as it's increasing in pressure, then the area has to come down. Conceptually, what it means is something, it makes sense. The air was flowing in this area here, right? And we are squeezing it and making it more compact, high pressurized. We are squeezing it. So the area it needs keeps getting smaller, 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 all the way to the smallest at the exit. This is why it's kind of doing that. And the exact opposite of what I said happens in a gas turbine. So this is why we do it the other way around. And for all of you who have that thought right now, I can see that thought in the brains of few of you. About 10% of you probably have that thought. You said, but if this is a hydraulic turbine, rho is constant, then you wouldn't plot it this way, and you are absolutely right. If I'm depicting a hydraulic turbine, there's nothing wrong to do it like that, just make no mistake. Nobody will tell you, like, hey, you made a mistake right there. Why did you make the turbine? No, it's a schematic. But you would be better, to be honest with you, it will actually communicate your depth of understanding. You will actually plot it like a box. You'll plot like a box and say, this is my turbine, if it is a hydraulic turbine. Because this concept we just discussed goes away, there's something else comes in. And, in the turbo machinery material that I will present, I may touch a little bit on the different types of hydraulic turbines, Pelton wheels, Francis Kaplan, and then you will know a little bit more about that concept of specific C, and things of this nature. Good. Little bit more on the devices. Now, when I introduced energy to you, I said there is the work side of things, spinning shaft, and I completed that. Two families, a family that spins the shaft and a family that needs a shaft to spin. Now there's the family that there's no shaft. It's Q. It works with Q, heat transfer. Or changing energy form. That's what's on this screen. So boilers or heaters, what they do, there's no work. In your basement with your boiler, no shaft spinning, none of that. You burn fuel, you heat the water up. That's it, Q. It's just Q. Take the energy of the fuel, change it to a thermal energy. We heat something up. Condenser and radiator is the opposite of that. It's when you want to remove heat, right? Think about your AC. It's removing heat from your home, then a condenser is involved. There's some sort of a condenser is involved. There's some sort of that heat exchanger that cools things down. It's more of called an evaporator, just to beyond what I want to say today, but it's that device that is pulling air from your home, right? Moving a Q. No, your radiator. In your vehicle, you have a radiator. As long as it's not an electric car. At least in that form. A radiator in your car, water is cooling your engine. It's burning fuel and the water is cooling it. And then what happens is this water, we need to cool it down. So we take it to a radiator, it goes in, we pull the heat out. Now we have colder water, we send it back to the engine to cool it back, and it keeps coming back and forth, right? Goes into the radiator to cool down. At some point in future, there will be a video about heat exchangers. We'll tell you more about how this works in practice. What's the radiator? We'll show you some pictures and we'll discuss more about it. If God gives us the opportunity to do that. Third element is the nozzle. Now, nozzles, what they do, it's not Q and it's not work. They change pressure to velocity or enthalpy to velocity. What do you mean? Well, you know what it means. You take your hose and you squeeze at the exit and you get a very large momentum jet because you wanted to send the water all the way very far away, the portion of your garden or whatsoever that you want to send the water through. You did that intentionally to just get high momentum and send the water. What you've done is a nozzle effect. You've changed pressure to velocity. these nozzles, you see the fire hoses for the firefighters. They have that tip that sort of goes like that, and it gives a very high momentum of water that they use to put out fires. You've seen a rocket with this, what we call conversion diversion nozzles, and they're doing the same thing. They are exchanging enthalpy or pressure to velocity to give you that high velocity that you need for a reason. The opposite of these are the diffusers. They are the opposite. They convert velocity to enthalpy or pressure. Not as common as the nozzles in our day-to-day life, because they are typically hidden from your eyes. See the compressors. Let's go back to the compressor now. You know how the compressor works? The fans, they spin. Now you have kinetic energy. You told me, yes, that's like the fan. You told me that the fan does that. It spins, gives you kinetic energy. And you said the compressor is a bit different. Now let me tell you why the compressor is a bit different. When it spins and you have kinetic energy, I don't want kinetic energy. I want pressure. So right after the spinning part, I put these passages that are a diffuser. It opens up an area, and now the velocity changes to pressure. I change that kinetic energy to pressure. And then I repeat. This is called the compressor stage. Spinning rotor, spinning blades, diffuser. Spin it, change it to pressure. And then repeat. Spin it, change it to pressure. Spin it, change to pressure. Spin it, change to... You have all these stages put together, and there you go. At the exit, you achieve the conditions you need. You get the fluid at the pressure you desire, if you will. Now, it's a very easy concept when I tell you a nozzle increases velocity. Everybody here knows. If m dot is rho AV and area is coming down, then V goes up. And the opposite is true. You have a diffuser. M dot is constant. The mass running through it is constant. So m dot is rho AV, and A is coming up, then V is coming down. So no confusion there about how the velocity is changing to pressure, if you will. And the way you will know it's changing to pressure or enthalpy is when we write down the energy formulation. So bear with me for a second. But what you know right now is the nozzle brings the velocity up, diffuser brings the velocity down. And in a second it will make sense to you that why, when this happens, the opposite happens to your pressure or enthalpy. Good. Now we are ready to write down the energy equation in a simple form. And once we put the simple form, immediately we put it to application on very simple example. Then we top it up a notch and we go to detailed system level analysis with the energy conservation. And then we top it up a notch to advanced analysis that you will actually see and use in the industry. And you will get subjected to some of that in your early career as an engineering student. Good. Now writing down the energy equation is going to be very simple. If I ask you, after what we have done so far for 1 hour, when a fluid is moving, what are the energies associated with that moving fluid? You will say there are three things: enthalpy, kinetic energy, potential energy right there. If a fluid is moving and I want to quantify everything it has, all in all, nothing else it can have, it will be enthalpy, it will be kinetic energy, it will be potential energy right there. H v squared gz. Where is the mass? Where is the m dot? Why aren't you multiplying? That's the specific energy form. Kilojoule per kilogram, kilojoule per kilogram, kilojoule per kilogram. That's it. Nothing else to put in. That's all the forms of energy that we can put in. Now, we also discussed that there is Q and work, so I did a schematic of a system here. This system can be your pump, your compressor, whatever the device or the system you're dealing with. I'm going to assume that the system, this is just an assumption. There's Q coming in, there's Q coming out, there's work coming in, there's work coming out. There's a mass coming in, there's a mass coming out. And we are going to call this device that we want to analyze our control volume, what we want to analyze. Now, if you go in practice, search for a device that looks like what's on the screen. You most likely will never find it. So what are we trying to do then? We are trying to teach you how to write the equation in general. Doesn't matter the device. If that device you are analyzing has 3 mass flow rate coming in, okay, use the same thing. 2 mass flow rate coming out, do the same thing. There's no Q coming in. There's no Q coming out. There's work coming in, but there's no work coming out. Just write it down the same way. So what is the way? We already said it today. We're already done. Energy in equals to energy out plus energy stored. Done. That's it. We're done. Where will the energy go? There's no way it's going to do anything else other than being in and out and stored. Energy in takes the following forms. It's either with the fluid or a Q or work, or all 3 or some of them. That's the total energy coming in. And the same thing for coming out. It's either with the flow, with the Q, or with the work. This is the stored energy. And E1 energy with the fluid, 1, is H1 V1 squared Gz. It has an enthalpy, kinetic, potential. This is the energy with the fluid coming in. This is the energy of the fluid coming out. This is the energy not associated with mass, which, as we discussed today, has 2 forms, either Q or work. And what comes out is either Q or work, and that's the stored energy. And there you go. Here is your energy equation for this system. If your system had 2 inlet masses, 2 exit masses, you're going to do that here. M dot 1 plus M dot 2 equals to M dot 3 plus M dot 4, and you add all the other elements as necessary. And immediately we put this to work, meaning we use it. Let's go and see how this will relate to what you learned on the first law of thermodynamics. So it turns out that the first law of thermodynamics is a simplified form of this, energy equation form that we've written. How is that? Let me show you. Assume it's steady state. There's no stored energy. Assume no work is coming in. Assume no Q is coming out. Assume that the potential energy change is about 0. There's not much difference in the potential energy. And there's not much difference in the kinetic energy. All these terms can disappear from the equation on the previous page. Plug everything in. You end up with Q minus work equals to M dot times delta H, H2 minus H1. And this is this formula right there. Q minus work equals to delta H. That's the first law of thermodynamics. Does it make sense? For now, I think it makes tremendous amount of sense for you. Says, well, the reason there's a difference between Q and work is actually the difference in the manifested the difference in the enthalpy. That's it. Let's put this equation to a few examples immediately here, right? A turbine. When somebody talks to you about a turbine, it's not a bad assumption to ignore Q. Why? Because you learned today that turbines are primarily devices to generate power, generate work. Not a bad idea to ignore Q and say it's of no significance here, don't talk about Q. So what you will do for the turbine, you will say energy in, that's H1, is equals to energy out, that's H2, plus the work. So the work is m dot times delta H. That's the power you get in kilowatts, for example. You want to divide by m dot? Absolutely. And you get it in kilojoule per kilograms. Let's apply that for a compressor. We'll say H coming in. Now don't forget plus work coming in. This work is coming in is equals to H2. So the work that you paid for the compressor is m dot times H2 minus H1. This was H1 minus H2. Let's go for a boiler. When I tell you a boiler or a water heater or a condenser, why would you think there's work there after what we've discussed today? These are devices that just transfer heat. There's no mechanical motion involved. So don't think in terms of work. You say, I had H coming in, I have Q coming in, I have H coming out, so the Q I paid is m dot H2 minus H1. That's for a boiler. If you go to a device that extracts heat, it's the exact opposite of that. You say, I have H1 coming in, I have H2 coming out, I have Q coming out. Q is being pulled out of your system. So Q is m dot H1 minus H2. Many people, when they discuss this topic, get some confusion of plus, minus, this, that. I strongly recommend say energy in equals to energy out. That's it. And you know if it's a turbine, that's work coming out. Fan, pump, compressor, work coming in. Boiler, heater, Q coming in. Condenser, cooler, radiator, Q coming out. But let's say they give you a funny device. Let's give it a name. The Zoffler. I don't know what that is, but let's say it's solve the Zoffler. And you say, oh, I don't know what to do now. Is this like, work coming in? Is this like work coming out? What does the Zoffler exactly do? He's not telling me in the problem statement. Well, in this case, it becomes very simple. When you try to do the energy balance, you still say energy in equals to energy out. That's never going to change. But then assume, say the Zoffler work is coming in, right? And do the schematic and say work is in, here's, this fluid is coming in, this fluid is coming in, and this fluid is coming in, this fluid is coming out. Put everything and solve the Zoffler. And if the work is positive, then your assumption is right. The Zoffler is using work, right? But if your assumption is wrong, the sign will be negative. Like when you finish your math, it will say, hey, it's, negative 100 kilowatts. Say, oh, as the Zoffler is actually generating work, right? Very highly unlikely you will get the Zoffler to analyze, but just in case. So it's very simple. This is very simple. Now, let's move to the pumps. Why say the pump different? Well, you will know in a second that the fact that it is incompressible we'll have a simplification to the example and we'll make things taste a little bit different in a good way. So this is a pump. Pump needs work. There's something coming in. This is water coming in. There's water coming out. When the water comes in with the certain m dot. It has h, it has velocity, it has kinetic energy and potential energy. We killed that. M dot h v z2. Let's write down the energy equation, the generic one. Many things, there's no Q out, there's no Q in, there's no work out, it's only work in. And furthermore, we can neglect the potential energy, we can neglect the velocity difference, assuming that V1 and V2 are the same. That's an assumption. It may not be, by the way, it may not be. You know, the potential energy difference makes perfect sense to ignore that for the pump. You know this pump, like if I have it here on the table, like, and it's like this big, this, you know, very large pump. And you look at the difference between, it's literally the immediate inlet. This is like the immediate inlet to the pump and the immediate exit of the pump. You say, well, these are very close. I mean, potential of what? Just, you know, compared to this order of magnitude, oh, this thing is moving tremendous amount of motor, tremendous amount of energy. It's, you know, many horsepower. It's like you saying, you know, I have $10 million and 2.5 cents. That doesn't make any sense. You don't do that. You don't do that, right? You have that feel for the money. Please use the same feel for the energy. You see, it just doesn't make sense. Don't talk about it. Good. So potential goes away. And I assume that the velocity is the same. That's an assumption again. You will see in a second that I will actually not use this assumption. But in this case, put everything together. Work of the pump is m dot times delta H. And you say, well, didn't we just do that with the compressor? We said the work compressor is m dot delta H. No, we're going to take this to the next level now. Isn't H U plus P over rho? By definition is the enthalpy. Let's do that. So we plug it in. And there you go. Here's the pump equation now. So pump power is delta P over rho plus delta U. But what is delta U? U is the specific, is actually the enthalpy. Now the enthalpy for an incompressible fluid is CV times T. So that term becomes CV delta T. Well, delta T is the change in temperature. Now pumps, it's a very reasonable assumption to assume that the temperature did not change. So that CV delta T just goes away. There's no value of saying CV delta T. There's no temperature change. So suddenly something fascinating happens right here. The work of the pump is simply the delta pressure over rho. Amazing, is that right? Amazing. Imagine you have a pump sitting here on the table. Pressure is measured at the inlet and pressure is measured at the exit. There you go. Take this pressure, divide by the rho, and there you go. That's the work of the pump. If you really want to get the power drawn from the electricity, a little bit more formulas will need to come into this, but this is great. This is a great starting point. Just the knowledge of the pressure. Remember, in my properties video, pressure is a direct measurement. I just put that sensor right there. Easy going is the pressure is the work. In 1 second, I get the work of the pump. Now try to do that with enthalpy. Enthalpy is not easily measured. It's not easy. It's not a direct measurement. You cannot do that. You cannot online measure enthalpy. So that's the goodness of making this simplification for the pump. It's something that we very easily measure accurately. Good. Now, we are going to talk about applying the conservation energy to closed system. Very quickly, just one slide. Now, it's not going to be any different from what we said. Energy 1 equals to energy 2 plus energy stored. Energy at state 1 is equal to the energy at state 2 plus what was stored in between. Put the terms. Now take a close look. I'm not using m dot. I'm not using mass flow rate. There is no mass flow rate. It's just mass. It's not changing, not coming in, it's not coming out. And when I express the energy of the fluid, I'm not using H anymore. Why? There's no flow. You don't use H, you use U. Internal energy, a fraction of that is what you use. Put it in. Q and work doesn't change. Q and work doesn't change. Here's the assumption of what's coming in and what's coming out. Do the magic like we've done before, same exact. Q minus work equals to delta U. So instead of saying Q minus work is delta H for an open system, it's delta U for a closed system. All what it is in one statement, you use U instead of H to analyze a closed system. Good. I want to talk to you to level up to some detailed analysis now. Now we are in the detailed analysis now where we are incorporating losses. I want to teach you all about that. So imagine you have that pipe running from the pumping station by the river to your home. Many miles of pipe, or you are pumping crude oil from where it's extracted to a refinery somewhere, or you are pumping natural gas in a line that is running, many miles. There is something important you need to know called frictional losses. Frictional losses are the losses because of friction at the wall of the pipe. Now that pipe, it's made of, let's say, cast iron. Let's say it's made of steel. Let's say it's made of stainless steel. Let's say it's made of some sort of plastic. Let's say it's made of glass. No, not that one that is, but this glass is what we use in a lab for some reason, for visualization, stuff like that. But what I'm trying to say is, as the fluid is running in there, it interacts with the surface. Where it interacts with the surface, this friction will reduce the enthalpy or reduce the pressure. And you can immediately relate to that. Let's say you are trying to push a fridge, a large one, in your kitchen. Let's say it's sitting on ceramic. Your floor at your home is made of ceramics. This tiles, ceramic tiles. You will push the fridge and you will feel with ease it's actually moving. I don't need to do much. I always need to push, but not much. But let's say it's sitting on a carpet. And you say, I need to push more to get it to move. That's exactly the case. That friction in the pipe is doing the same thing. I need to move the water. It has friction interaction with the surface. I need to push it so it can just go. And when it goes, you're going to lose that pressure you've given it. Let me tell you exactly what I mean. Let's say this is the water coming from the river and this is your home. And this is the long pipe. And I put some numbers here to build you a feel, give you a feel. So we measure the pressure right after the pump has energized the flow. It's 100 psi. And the water is flowing until it reaches your home at 70 psi, where it has lost on the way over a distance of 10 miles, about 30 psi. That's the story of friction. See, the water was energized here. It's coming out with energy. And as it flows, it's losing this energy. It's losing its pressure because of the friction with the wall. It's called frictional losses. And by the time it goes there, here the energy was 100 psi, like the pressure is some form of energy. And it went to 70, so you say, where did the 30 go in frictional losses? The 30 went in friction. I had $100, now I have 70. Where did I spend the 30? In the friction, to overcome that friction. Now, this pressure loss is beyond what I want to discuss in this presentation, but very quickly, here is a formula for it. This is the pressure loss due to friction, and the terms involved in this formula is diameter of the pipe, makes sense, length of the pipe, makes sense, velocity that the flow is moving with, squared, take a look at that, it's proportional to that squared, and something called F, the friction factor. You plug all these together, I give you a tube, has this length, has this diameter, I give you the Q, you plug them in, you get the pressure loss due to friction. Most of you will say, length I understand, diameter I understand, even velocity I understand because you tell me I'm moving 3 gallons a minute. Okay, that's Q is equals to A times V. I put in the area of the pipe, it's a 2-inch pipe, I get the velocity. All done, all set. I know the elements, I can put them in, I can estimate them. But what is F? F is a friction factor. This is the number that expresses the friction with your tube, and you can immediately, and you'll be thinking, right, if you say, well, if it's made of glass, that's not going to be much, as if it's made of cast iron, and going to be a little bit different. It's made of, stainless steel, and it's going to be a little bit different if it's made of, plastic, and it's going to be a little bit, and on and on and on. There are charts and equations, formulas for that F, beyond what I want to discuss today. But now you have a feel that I can actually calculate that loss in pressure with some sort of this formula, if you will. You can relate. When you get a straw, you are trying to drink water with the straw. If the straw is very small, you need to suck really, really, really hard. If the straw is bigger, you don't need to suck that hard. Diameter and velocity. You immediately calibrate to it. Oh, now I have a feel. See, they make this shake. Chocolate cake shake. Now, this, I don't know if you've seen this before, but what happens is they actually take a chocolate cake in the blender. Do you imagine chocolate cake? And you get that thing. Now the straw. Now, what will happen if you try to put a small straw? You're going to keep sucking and you won't even be able to. Because the frictional losses, the density is extremely high, everything is sort of messed up, right? How can you put enough to overcome all this and be able to pull through? So the straw is very large, just like a finger, a finger large, and that makes it. Now you can suck and pull that chocolate cake. Good. Let's top it a notch. We are in the detailed analysis here. We're going to top it a notch. I'm giving you a system on the screen. Let's start with that. What is this system? It's a typical depiction of how pumping systems work. There's a pump sitting on the ground. That's our datum here. The word datum immediately tells you that we're going to be using potential energy, because datum, then potential energy relates to that datum. So here's the datum. There's a tube sucking, like your straw. This is your straw. Sucking the fluid, in this case, let's say it's water, from down here where the water is. And let's say this is your skyscraper that you live in, very long, and the reason we have the pump is to suck that water from there and pump it all the way up. Let's say very long skyscraper. To a tank sitting on the roof. And then this tank sitting on the roof, so water comes out, dumps in the tank, fills that tank. Then that tank feeds the whole skyscraper. Tremendous amount of water. Let's say it's a very large one, 200 gallons a minute. Something really large. This is called the suction. Your straw, where you are sucking from. When you suck with a straw, you pump in your stomach. That's not the case here. You pump to the delivery in the tank. This is called the delivery configuration. This is the suction configuration. The water level sits at H suction. This is a water level. You know what the water level means? This is 3 meters. Something of this nature. The water is down 3 meters. H suction. And this is where your tank is up top on the roof of the building. So let's say this is 50 meters. 100 meters. Tremendous. Whatever the number is. We call this H delivery. Static delivery height. Just the height. The tube length, your straw length, is L suction, and your delivery line is L delivery. When you suck, this tank is open to the atmosphere, so this water level is seeing atmospheric pressure here. The same happens to your delivery. When the water discharges, just imagine like it's literally here. If you're standing here looking at it, it will be just the water is flowing. It falls and fills that tank. It's free fall. So the pressure right here at station 3 is atmosphere. It's discharging in the atmosphere. Station 3 is here. Station 2 is here, right immediate at the exit. Station 1 is right here at the inlet. And station 0 is down here. These are the different stations involved with this problem. Let's apply the energy equation that we learned today on the suction side of things. Pressure plus potential plus kinetic is equals to pressure plus potential plus kinetic plus the losses you lost along the way, losses due to friction. There is no work, there is no Q. Remember, I'm applying the equation from 0 to 1. I have nothing to do with the pump. I don't care about the pump. 0 to 1. But when you do that, this is atmosphere, it goes away. Pressure here. Velocity goes away. You say, why is that? Why did the velocity go away? Maybe there was a little bit of velocity. Sure, and if it's a little bit, you can ignore it. Imagine you are pulling from the river here. Imagine you are pulling from the river. And think about that for a second. Do you think that very large water surface moves with the speed that compares to the speed in your pipe? Let me say that again. Continuity equation tells you that mass flow rate is the same. Rho AV is rho AV. In this case, it's water. Take the rho out. AV is equals to AV. So the area times velocity has to be equal to area times velocity. Let's say this is a 2-inch pipe. So that's your area. And it has a certain velocity to it. And let's say this is the tank. You see the area ratio. This area of the large tank, the river, the velocity is what? 1/500. Then there's no need to think of this velocity, you say it's about 0 for this example. How about if I give you another example? Just I always want to make sure that we are well connected. I give you another example where I actually give you the velocity. So where the water surface velocity is moving at half a meter per second. Okay, then use it. I've given it to you. Then use it, right? But why don't I give it to you? Because the area ratio is largest negligible. You can take it out. So this goes out. This goes out. Why is this negative? Why didn't you just say rho GH, right? And by the way, I say rho GH, I say GH, I say H. These are all different forms, and all what happens is you divide. Either you keep the G, you divide the full equation by the G, you keep the rho, you divide the full equation by the rho. Remember, it's one equation, you can multiply and divide, and we use this trick for some reasons. So why is this rho GZ, which is just Z in this case, is negative? Well, because I put the datum here. This is my datum. And if it's lower than the datum, it's negative. If it's upper than the datum, the potential energy is positive. Potential energy is positive if you are up top here. If it's negative if you're down below here. Let me tell you. How about if you, when you solved this problem, you did something different? You said, no, this is my datum. I'm going to use it to solve it this way. And this point will be HD plus HS, and this will be 0, and great. You will reach exactly the same conclusion that I have here. It's not going to change. It doesn't matter. Those things, they don't matter. Whatever the way you analyze it. Good. And at station 1, I have the pressure velocity H lost due to friction in the suction line, right? And I plug the numbers in, and I end up with P1 equals to this formula here. The pressure at point 1 is the negative of the summation of this lift. We call this the lift, where you lifted the water from, called the lift, right? Suction lift, in this case, this is where you lift it at the suction. V squared over 2G plus the H friction due to suction. This is a formula for P1 over rho G. By the way, gamma is rho G. I want to make sure everybody is calibrated. Multiply this whole equation by G. Okay? P1 over rho, GH, V squared over 2, GH suction. Let's multiply the full equation by rho G, gamma. P rho GH, rho V squared over 2, rho GH. Good. Let's apply the same equation between station 2 right at the exit to station 3, right here. And for a second we will assume that this line is a constant diameter line, meaning the diameter of the pipe at 2 is the same as the diameter of pipe at 3. What does that mean? Well, area is the same, so the velocity is the same, right? So V2 is V3. So we can take that out. And Z2 minus Z3, this distance here, is H, delivery. Plug that in. And now you have a formula for P2 over gamma here. P2 over gamma is H delivery plus H suction, H friction on the delivery side. Now you are thinking, why did you get a formula of P1? Why did you get a formula of P2? Let's see why. Let's apply the energy equation between 1 and 2. Now the pump is involved. Now the pump is involved. We're going from 1 to 2 and the pump is involved now. So it turns out this will be the equation. Where is the GZ difference? We've discussed that before. This is the same pump. These are very small differences. You take them out. There's no difference in the Z. So the work of the pump is P2 minus P1 over rho plus V2 squared plus V1 squared over 2. Now you will say, but earlier in this presentation you said work of the pump is P2 minus P1 over rho. No. When I said that V1 is equals to V2. And this is why it turned out to be like that. How about if V1, the velocity here, is not the same as V2? Well, that's the difference. And I actually even said that comment when I put it there. This energy equation is extremely simple to write. All what you need to do, write it down and put exactly what is considered and what needs to go away. But I have a formula for P2 and a formula for P1. Plug it in. From the previous slide, you end up with this formula. And this formula becomes a very interesting formula. It says take the H static suction, the lift at the suction, and the lift at the delivery, H static delivery, this elevation difference, sum them up. Plus whatever you lose in the suction and whatever you lose in the delivery, H friction delivery, and add to it the kinetic energy at station 2, and that's your pump work. And because this is a distance and this is a distance, they sum up together and they call it static head. And it's actually a very nice concept. Think about that. Think with me. Think with me for a second. Why did engineers do that? To analyze pumps. Think about that. If you go there, you are the engineer visiting this site, you are going to analyze this and build the system. You know what you will tell yourself? Here's the way you will think. You say, okay, I have the water sitting here. I want to take it there. I want to move the water from here to there. I need to lift it from here to there. That's it. That's your static head. And this is 100 meter. I need to lift it 100 meter. But I also have to pay for the friction here, that straw. I need to pay for that friction. And I need to pay for that friction. I need to pay for the friction in the suction, for the friction in the delivery. So my pump has to pay to bring the water 100 meter up, plus the friction in the lines, plus the kinetic energy in the delivery line. Let me go back again one more time, because we will kill this. Why didn't we keep this equation as P2 minus P1 over rho V2 squared and just plug it in there? Well, I think you know now why. See, this equation relates to what the pump needs to do with the system configuration that you have. Meaning, it's an immediate formula that tells you if this is what you are trying to do, bring the water from here to there, this is your, line. You measured your lines, you know how the lines were run, you know the length, you know the this, that, FLD, V squared over 2G, you know how do you calculate the friction, as we discussed. It immediately takes you there. However, the outcome is the same. But engineers, what they do is, when they have an application, like a pumping application, and that's what I'm doing here. All this detailed analysis is I'm going very detailed on how you analyze a pump system. They don't start from scratch every single time they want to analyze, let's write P2, let's write P1, let's write the energy equation now, let's substitute, let's take it now. Because by the time you are doing that, there's another engineer who said, okay, we need to lift the water 100 meters. What's the length of this pipe? It's X, and the delivery pipe, this is 150 meters. This pipe is, 10 meters. It has this bend. The friction, plug the numbers in, here you go, and you are still applying, oh, let's apply the energy equation, let's put 1 and 2, we put formulas that we can put to use right away, right? But the goodness of understanding the ins and outs and the bolts and the nuts, and if there is a concept I want you to take from all my videos, that is the concept. You will be an extremely good engineer, way better than the typical engineer, if you can always go back to the first principles and arrive at the same concept. You will be an amazing engineer. So let's keep going. So what's Bernoulli equation? It's the energy equation applied on a moving fluid with some assumptions. Take a look here. Here's a moving fluid. And I pick a station. This is 1 and this is just 2. Any 2 stations. And at 1, let's assume there is a V1, there is a Z1, there is a, right? And at 2, there is a V2, there is a Z2. And let's assume there are no losses. This is an assumption. I'm assuming there's no losses. And let's assume, as we have done a second ago, there's no power extraction, power addition, heat generation, none of that. Write down the energy equation now. And assume that this is incompressible. You remember what happens if we assume incompressible? You say H plus V1 squared over 2 plus GZ is equals to H, but H is U plus P over rho, but U is CV times T, but temperature didn't change, take that out. Now with pressure I can write it down instead of enthalpy as pressure. You arrive down here. Bernoulli equation is where you make all those assumptions I said to write it down this way. Instead of saying enthalpy, the kinetic energy plus potential energy is constant, this just means they are constant. Energy has to be constant. Where did it go? Instead of saying enthalpy, you use pressure. Why? Because this is an incompressible. So you can use pressure instead of enthalpy. And you say the sum of 3 is constant. Let's simplify it more to arrive at a very powerful concept. Let's say that the Z did not change much. Elevation is not much different. Take the G delta Z out. Here's what it looks like. Now, this is very powerful. Right there is very powerful. It says that when a fluid is moving, pressure and velocity, energies, their sum is the same. Pressure energy, P over rho, plus kinetic energy. Their sum is constant. If the velocity goes up, pressure comes down. If the velocity goes down, pressure comes up. Extremely powerful. Let me tell you, today I spoke about nozzles and diffusers, and I told you at the time, bear with me. It's easy for you to understand that when the nozzle comes down in cross-section, see, m dot is rho AV. As the area comes down, V comes up. Straightforward. Diffuser, area comes up, velocity comes down. Straightforward. But I told you then, a diffuser increases pressure. A nozzle decreases pressure. I told you, bear with me until I talk to you about the energy equation, and now you know why. Now you know why. Why? Because the pressure, energy, and kinetic energy summation is constant. If the velocity, one more time, if the velocity in a nozzle comes up, pressure comes down. The sum has to be constant. It's almost as if you are saying, listen to this very carefully, velocity is coming up on the expense of pressure. Pressure is paying for velocity to come up. A diffuser, velocity is coming down, and it's giving you high pressure now. Pressure is coming up on the expense of velocity. The velocity is paying for it, so the pressure goes up. And now you know how the diffuser and the nozzle works. You see this diffuser or nozzle. Is it a reasonable assumption when you look at the firefighter nozzle tip to say that the losses there is ignored? Absolutely. Absolutely. When we spoke about the pressure losses in pipelines, we started talking about, like, long tubes and, long pipes and things of this nature. Well, this nozzle losses, frictional losses, compared to the kinetic energy level is negligible. How about if I want to incorporate it for any reason in the world? Like, I want to be very accurate and I want to apply this equation to that nozzle of the firefighter, and I will say P1 over rho plus V1 squared over 2 is equals to P2 over rho plus V2 squared over 2 plus the losses on the way. And I will estimate the losses and I'll put it in and I will get the V2 that is accurate. I'll bring the actual velocity coming out from this nozzle to be accurate. Try that exercise. To your surprise, you will find out that ignoring it made you 99% correct. The best engineers I've worked with, and this is what I want you to be, even if you are a 60 years old professional engineer, it's not too late. The best engineers I worked with can very quickly do order of magnitude analysis. All right, this is very big, this is very small. It's like when you say, all right, I'm asking, how much money did you make this month? So you say, I made, $10,000. Well, you didn't tell me it was $10,000 and, 3.5 cents. Because you immediately were calibrated. What does it matter? What is 3.5 cents? It is $10,000. We don't talk this way. Now, likewise, there is a way in engineering that you talk that shows that you are unbelievably powerful in understanding the concepts, what to add and what not. The difference, listen very carefully to this, between the one who will use this equation to get the velocity at the exit of the nozzle. You will ask the person, give me the velocity at the exit of the nozzle. He goes on the 2 minutes. Here's the velocity. Then there's the other person who does not have a good understanding of engineering concept. He is a person who is not taught well. You tell him, give me the estimate. Say, okay, give me a couple hours. I need to be accurate. So the first person you give the task to, he took 2 minutes. All right, boom, here's the number. Thank you. The other person, he said, give me a couple hours. He went there for truly a couple hours. And he comes back after, 3 hours. Yep, I solved it. You tell him what was the velocity. He tells you the velocity was 222.365 feet per second. The first person told you the velocity is 232 feet per second. Which one will you work with? The one that said 232 all day. I do not want to work with the other one. You are wasting my time. You are wasting my resources. If you are an employee in a corporate, you are wasting the corporate money, resources, and time. You are an engineer. Engineers do order of magnitude analysis. They know what to include, what not to include. Very good. Let's stop at a notch. And now we're going to go to advanced analysis, even a little bit more advanced. Some supplementary materials here are good for you to review, so please take the video of my combustion introduction. This is my deep expertise. I love that science. And watch other couple videos about properties. You may need that to understand what I'm gonna explain here. Now, let's say I'm gonna take that element from the combustion system, please watch the video, called the premixer. All what it is, it looks complex, but air flows through it. Looks like that. You know, have passages, there is a reason for that, see my video. And the air flows through it. So here's the experiment I'm gonna do. I'm gonna take that device, I'm gonna put it in a chamber, like literally a chamber. And this chamber has air coming through it, and this air is metered. Metered means I'm measuring the mass flow rate. I know the mass flow rate accurately, m dot. Air goes in, it fills this plenum at a pressure P1, and it flows through and it dumps here in another plenum at a pressure P2. I have another plenum sitting at the exit of this element, and air is just going there. You know, you turn it on and air is coming and it dumps out. What are the things you are measuring on this test? I'm measuring m dot, I'm measuring P1, I'm measuring P2, I'm measuring temperature. Good. Let's write it down. Applying the energy equation on the starting point between point 1 and 2. P1 over rho plus V1 squared over 2 equals to P2 over rho plus V2 squared over 2. V1 is about 0. And you know that trick, we've discussed it before, right? We said when the room you are sucking from is a large plenum, there is velocity, but it's low enough to just ignore that. So I can take this out. And this means that V2 has a formula now that looks like this. This is the formula of V2. And the density I'm using in this case is I'm using density 2. If the density is not changing, like rho 1 is equals to rho 2, like you're running water, okay, just use rho. Don't worry about 2 or 1. If it is air, which is compressible, what's going to happen is truly the rho 1 is not the same as rho 2. Station 2 is very tricky in this experiment, so bear with me. Station 2 is roughly here somewhere. It's not here. It's not here. This is not station 2. Station 2 is here somewhere. At station 2, the density is rho 2, the velocity is V2, the area is area effective. We call it area effective. We don't say area 2. That's the whole point, but bear with me. We call it area effective. The flow has already expanded. You say, what do you mean expanded? Well, there was a large pressure here, and this pressure pushed the flow, and it dropped to P2. This is called expanded. The pressure dropped to P2. Well, that difference between the pressure here and here, what you are measuring is we are ignoring that for a second. We are saying that this pressure is similar for a second. And in a second, you know why it doesn't really matter for this particular method and what we are trying to do. Doesn't matter, but I want you to know that you use rho 2 after it has expanded to station 2 if the density is important for you. If density is important for you, use the rho as rho at station 2 where you've built velocity and the density has dropped. Compressibility effects are important here. You take quite a bit of pressure difference. That the rho is equals to P over RT, you'll start to see a difference in rho that you cannot ignore. Good. We've killed this. V equals to square root 2 delta P over rho. If you are a good engineer, you know what that is. I have worked with professional engineers. They didn't know that if compressibility is to be not ignored, it's important, you have to use rho 2. I kid you not. And it makes a difference in the accuracy of this calculation. Now, we have an equation for V2. You know, this V2 is the hypothetical velocity here somewhere, this hypothetical velocity here somewhere, right? So m dot is rho AV, rho VA. What is area effective? That's the whole reason we are doing this analysis, is this area effective, is the whole reason we are doing this analysis. This area effective constant. Well, let's continue for a second. Just say rho VA. Plug everything in and get a formula for area effective. Now, think with me again, one more time. Look at this formula. Aren't we measuring m dot on this test? Yes, I'm measuring m dot. Good. Are you measuring P1? Yes. Are you measuring P2? Yes. Can you calculate the rho? Yes, P2 over RT. Okay, good, you have that. You have rho 2. Yes, you have everything. Now you get an area effective. You were able to take a very complex element. These elements can look very, very complex. And say, you know, this is 1 inch squared, for example, 2 inch squared, 3 inch squared, 1.5 inch squared, a number, area. Why is this important? Why is this something that we like? What are we trying to do? Think with me now. You were able to say, this element have this area. If I put pressure on it P1 and there's a pressure P2, I can now estimate the flow. Take a look here. Imagine I take this element that I tested on a flow stand in a very simple flow, and I put it in an aircraft engine with many other elements and whole lot, quite a bit of stuff, and the engine is even flying or whatsoever. And I want to meter the flow. I want to know the flow when it's running. I want to know how much flow is running. Here's how you can do it. Take a look at this formula here, m dot. Rho 2 square root 2 delta P over rho 2 area effective. Do you know the area effective? Yes. Do you know the pressure 1? Yes, I'm measuring pressure 1. Do you know pressure 2? Yes, I'm measuring it. Now you have an m dot. So you know the mass flow rate by just measuring the pressure. Area effective concept is a concept that allows you to measure mass flow indirectly by just measuring the pressure. Very powerful, extremely powerful. Just think about that for a second. But there is actually even more important reason we do that. There's more important reason. It's not only to meter the flow, it's to know how the flow is split. Now let me say again. Imagine this is a combustor or a jet engine, and we have many of these small units, and another unit called the heat shield, and another unit called the liner, and another unit called the nugget, and another unit called the phase stage nozzle, and another, quite a bit of stuff. And I want to know the air that is coming from the turbo machinery, from the compressor, the overall air coming in. I want to know how it splits. There is 30% there, there is 35% here, there's a 30% there, there's, right? How do you know that? That same exercise I told you. You take every component, and instead of it, you have an area effective, and you have pressure nodes. You know, pressure nodes mean what's feeding it, where it dumps, what's feeding it, where it dumps, what's coming in, where it dumps. And you make a network. Like here, you can use this commercial software, Pipe Flow Expert. And you can do that for even a piping system. Let's say you have a tank, there are 3 pipes running, and then they divide into 4, and there are valves sitting on the way, and this, I want to know how much water is going to this line, how much water is going there, how much water is going here, how much air on the, how if you want to split, they call them flow networks. You go to a software like this, you feed it the effective areas that you measured, you feed it the pressure points, you hit solve, voila, it tells you there's 30% here, 35 here, 20% here, 10 here, and 5 there, and you are done. You got your flow splits. Excellent. Good. And we are done. And we can conclude. It's been a great presentation. Boy, it's going to the 2 hours now. Very simple. Conservation of energy. Energy comes in is equal to energy comes out plus energy stored. Remember that energy takes three forms. If it's with the moving fluid, it's enthalpy, it's velocity, it's potential energy. There's Q and work. Remember your devices. Turbines, they generate work. It comes out. Compressors, pumper, fans, they take work. Boilers, heaters, they take Q. Condensers, radiators, they lose Q. Diffusers and nozzles, they exchange velocity to pressure and pressure to velocity, enthalpy to velocity, velocity to enthalpy. And we looked at applications, how to write it down for a pump, how to relate it to the pump system configuration. Don't forget about the losses that happens in long pipes. When the pipe is not long, when you are right at the inlet of the pump, you tend to say this is of no significance. Potential energy, when you take it out, when you keep it, velocity changes. We've known how to extract from this general equation the Bernoulli equation, a simplified form. The Bernoulli equation was tremendous in helping us understand the concept of velocity changing to pressure, pressure changing to velocity. We discussed some advanced concept of how to take a complex shaped geometry and express it in an effective area, right? We discussed the flow networks and how this is used to split the flow on a structure. And that's about it. Thank you so much. Don't forget to like and subscribe for more videos in the future. And take care and talk to you soon.